Wednesday, the 20th of August 2025. I want just to explain the hardening and tempering of steel and the heat treatment of steel. Now, what I have here is the tine of a hay bob rake, and it broke. And the reason, in my opinion, it broke is it wasn't properly tempered. It was hardened and it wasn't properly tempered. Now, what you're seeing here is what I believe to be martensite, martensite, martensite. And do you see the crystalline structure? I'm holding a lamp up here. You see the crystalline, do you see that grey crystalline structure? Do you see it there? Now I have a white garment here to try and emphasize it. Now watch this. Do you see the file? The file nearly barely scratches it, okay? Basic iron has the chemical symbol Fe. It's 26 atomic number. And on its own, it's iron. It's iron. I'm not sure if you're seeing me. I'm kind of getting down here a bit, but I'm using the back of the camera. On its own, it's iron, right? Iron is not that useful on its own because it's too soft. So really, you can get iron if you want it for a specific purpose. You really wouldn't unless it's a chemical experiment or something. Now, you can add a lot of other metals to iron. You can add lead, would you believe? Aluminium, molybdenum, tungsten, nickel. And on the periodic table, there's nickel, iron, and cobalt. And they're magnetic. And one of those has 25 atomic number, the other has 27, and Fe, iron, is in the middle. But the three of them are magnetic. So they're very close to iron, but we're dealing with iron here. Now, one thing that iron can absorb is carbon. Carbon. We're made partly of carbon. You can check it there. I don't even think it's a metal at all. Anyway, it doesn't matter. But carbon is what makes diamonds. And carbon is one of the hardest materials known. In fact, a diamond is the hardest material known. It's not normally used in ordinary lathe tools and chisels. It's more used in tools to cut ceramics, like tile cutters. And they spray it along the edge, and it can be used that way. But it's not normally used for a tool. Now, as you add carbon to the iron, you change its name. There's a degree of carbon you put up to about 0.4% or 0.04. 40% of 1%. Up to 0.04, the official name of it is perlite because there is carbon. But the carbon is insufficient, it's not in enough amounts to have any effect. It simply adds a slight bit of resilience to the steel and makes it a wee bit better. Moreover, making iron and steel, there's always a bit of carbon in the process, and there's no point taking it out because it's no harm. Wire nails are mild steel. The girders you see putting up a building are usually mild steel. The carbon content of that would be normally 0.03%. Whenever we get that right, 0.03 or 0.3%. That's 0.3 of 1%. So we can ignore that. You can't harden, harden or temper that type of steel. Even though it's officially called perlite, it's really more treated like ferrite. So you can case harden it by adding carbon to the outside of it, but it's only skin deep. Now, when you increase the carbon content above 0.4%. That's 40% of 1%. You then have proper perlite. So the jury's a bit out on whether you can call the lower carbon steel perlite, but you have perlite. P-E-R, perlite. P-E-R-I-L-I-T-E, I think. Now, I'm not going to be caught on spelling here. My job here is to let you know the science, not to be a spelling expert. You can get an English teacher for that. Perlite. Now, all steel with carbon in it is perlite from about 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1%. Now I'm talking about 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, or if you're talking about percentage, which I will, 5, 6, 7, 8, 9, 9 of 1%. Okay, now I know maybe I'm confusing you there, but when you get to 1% carbon, you have a very popular high quality steel. And if you take stubbed silver steel or electric arc furnace made steel for very specific purposes, like for example medical equipment, etc., it may have other additives, but it's usually 1% is taken as the optimum. If you wanted very hard tools to wear but without too much abrasion or too much strength, you could go up further, and you can go up to about 1.5%. As you get up above 1.5%, you're into problems. The steel cannot absorb enough of the carbon. If you go up to 2%, you might get away with it. If you go up to about 2.1%, you're into cast iron. And the steel is so crowded in cast iron that it forms flakes between the little, you don't call them molecules, the particles. Flakes. Like a bit like if you had a sheet of plain paper and a plain typing paper, and you mix concrete and you put the sheet, a little bit of concrete, you put the sheet on top and you put more concrete on top. You might cause the first piece of concrete not to adhere to the one below. And when you'd lift it up, you'd have two pieces of concrete. It forms a little barrier. Cast iron is in a different category altogether. It's very high in graphite or carbon, and it's very resistant to weather, and it can be shown on the spark test, which I may do. It's used for old draining pipes and things like that, and gutters, all of that. Okay, that's cast iron. We're not talking about either ferrite or cast iron. We're talking here about carbon steel, or in various amounts, or perlite. Okay, perlite. Now, if you can imagine a chocolate cookie, or indeed, those scones you buy with the raisins in them, with the dried fruit. Well, if you can imagine a chocolate piece, like in a cookie or a biscuit, one of those chocolate biscuits, throughout a scone, the wee bits of chocolate are separate in there. If you heat that scone, the chocolate will melt and it'll dissipate through the pastry. And if you turn it round, gravity will pull it down the other way. When you heat perlite or carbon steel, it reaches a point at about 710 degrees centigrade where the carbon is in little pellets, little pieces. So again, in perlite, the carbon is like the chocolate in the scone or the biscuit or the cookie. When you heat it up to a certain point, about 710 degrees centigrade, the carbon dissipates. It moves from a particle, point carbon, to a solution. Now, strangely enough, you may argue there's no such thing as a solid solution. Well, there is. It moves into a solution, but it doesn't do it without extra energy. And if you measure the temperature of the steel as you heat it up, at a certain point, we'll say 710, not to be exact, it stops heating. And what happens is the energy goes into shifting the carbon from the pellet stage, from the little particle stage, into the steel into solution, so that the entire steel is wrapped in carbon. Now, talk about tailor-made for human beings and man. This world of ours has to be agreed. It's made for us. Everything works. Right? So now, when it goes above that, I had the word there in the last video and I lost the video. Incandescent. Is there a name of something like incandescent? Escandescence. I just haven't it here. Anyway, we can print underneath. But when it goes above that point, it's called the critical temperature. A much better word. It goes above its critical temperature. And that's used universally. The other is only a fancy word. It takes extra energy. It stops heating for a minute. The carbon dissipates right through, making it into a sort of solution. Once it goes above that temperature, it's now glowing hot red. A magnet will not stick to it. It loses its magnetic properties. At the lower temperature, magnet sticks. You know all about that. You know what a magnet is. Above it, it won't stick. So therefore, you can use the magnet test. You can have a small, strong magnet on the end of a stick, and you can touch it to it, and it won't stick when it's above the point. Now the carbon is dissipated through the steel. It's in solution. Once it goes past that stage, the name for it is austenite, called after a fella called Robert Austin, who discovered it. It's austenite. It is of a different quality to perlite. You cannot have austenite except above the critical temperature in normal circumstances. Great scientific efforts are being made to make particular steels where the austenitic phase or austenite can exist at room temperature, but we're not going there today. When you have it above that temperature, it's austenite. If you let it cool slowly, as it goes back through the critical phase, you can see it still glowing. You take away the heat, it glows for a good while, perhaps a minute and a half. It can't get back to the lower temperature because it has to recrystallize or reparticular. It has to convert the dissolved carbon to little pinpoints of carbon, like the scone. Now with the scone you can heat it and dissolve the carbon, but when you let it cool, the chocolate still stays in the scone. With this steel, that's not the case. It can go up into austenite and return to perlite, provided you put in heat and provided you take away the heat and let it cool to room temperature normally. And so it goes from perlite to austenite. You let it cool, it goes back to perlite. No big deal there. Perlite with about 1% carbon is slightly tougher than nails. I've worked it and it's a big debate, but I think it's slightly tougher. The carbon does make it slightly tougher. So if I was making a critical component, I'd like it to have at least 0.6% carbon rather than just soft like a wire nail. But there may be circumstances where you might want it soft, so it depends on circumstances. So now, if you're buying particular steel, it'll give that if you buy from the big houses that supply it. Now, you have that so far. Now I can't see myself. I mightn't even be recording here because I can't see the other side. Anyway, supposing you take the austenitic high temperature steel, we'll say it's 730 degrees. After you get it through the critical stage, you can heat it till it melts. You get it up to 730, it loses its magnetic properties. If you plunge it into, we'll say, a medium like water, you stop it returning and you trap the solution in the iron. And what I've showed you there in the early stages is that's what happened in that there. That's trapped and it was too hard. Now when it returns from austenite through its critical temperature, it goes back to become, If you cool it slowly, it goes back to perlite. If you plunge it into a cool medium and freeze it quick, it goes from austenite to martensite. Martensite, I think it is. Okay, so you have perlite, austenite, martensite. When it's in martensite condition, don't ask me for what the word is. When it's in that condition, it's extremely hard. And the grain is very noticeable. I tried to show it to you there because it's not often I get an example of it. I kept that because I broke the tines on the hay bob. And it broke in the field, but that tells you why. So you get that white, grey, silvery, crystalline structure. It's very obvious to anyone with reasonable sight. And that is martensite. And that has been cooled quickly. The carbon is right through it. It causes that crystalline structure. And it's very hard. And you saw there, I ran the file on it, and you saw how hard it is. So martensite is austenite below the critical temperature, with the carbon spread out evenly, still in a form of solution. And a bit like the chocolate lumps are still in the bun. So essentially, if you heated the scone and the chocolate dissolves right through the whole pastry, when you cool it quickly, that's what you have. So when you break the martensite, that's what you have. When you break the pastry, all the chocolate's gone all through it. Is that a good example to give you? That martensite is so hard. It's unbelievably hard. I can't really think of any point where you need it that hard, but there may be ones. Now, so the next thing that has to happen is you have to temper it. And tempering happens because you add heat below the critical temperature. I think, don't quote me, I think it starts off at about 280 degrees Fahrenheit. And the funny thing about it is, if you take this screwdriver here, we'll take this wrench here. You have it now. If you grind it and have it shiny, as you put in the heat here, the colours will develop here from a very pale straw right up to a dark blue. And they'll travel up here, and that indicates the oxidization of the martensite, and it also shows that there's a change taking place in it. When you heat the martensite, you convert some of the martensite back to perlite, and they're mixed rather evenly through it. And this is unbelievably useful because the perlite is not as hard. It's a matrix thing, it's technical. And essentially they're leaves, like a heap of paper leaves on top. So you have perlite and martensite. And a little heat is mostly martensite. If you increase the heat, it goes back, some of it goes back to perlite. So martensite is capable of reverting to perlite. And if you heat it so much, if you heat it that this gets almost black, even though it hasn't gone up past the critical range, you have a form of mostly perlite, which has relented or given up some of its hardness. You've only a tiny, maybe, I don't know the percent, we'll say 10% martensite. And because it's mixed with the perlite, it can be beaten and it becomes malleable. If you only heat it a certain amount, you mix the martensite with the perlite and you have like a chisel. So this is tailor-made for man. And understanding this is a great thing to know, right? If you heat it too much but keep it below the critical temperature, you'll have a high proportion of perlite, which is just a resilient carbon steel. If you heat it only the right amount, you have the right mix of martensite and perlite in layer structure. And so you get toughness. You get toughness in it, depending on how much heat you put in after the critical stage. Are you with me now? Now, if you take I had a file there a minute ago. See, I'm stuck here because I can't hit the button to pause. But Anyway, we not go. You just take an ordinary file. It's high carbon steel. It might be 1.3% carbon. It's heated up to its martensite stage. It's shaped and all, and then it's cooled. And it's cooled quickly, whatever medium, and then it goes back to, it becomes martensite. It's tempered a slight amount in a proper furnace, and then it's probably only tempered maybe to a pale straw. If you want a spring, you have to go to a light blue. It depends on how tough you want it. A cold chisel for banging rocks would probably be cooled, would be heated up to maybe a deep brown stage. Are you with me now? So that's hardening and tempering. In America, the process is can be known as tempering and drawing. So just be aware of that. I think most Americans now use the term hardening and tempering, but in America sometimes they'll say tempering and drawing. It's just the big ocean there. So you understand hardening and tempering. Now, so you know now the science behind it, and we can maybe go off and do something. I'll go around the other side. This is very important that you understand this. This means you can make tools, you can make lots of things, and you can get very hard tools. Now, what you cannot do is produce high-speed steel. A drill bit like this requires up to 2,000 degrees to get it to harden. There are materials here to stop it being affected by temperature. So if you're going into high-speed steel manufacture, you have to have a specific way of doing it. But for the ordinary workshop and for most things, 90% will do using this type of heat-treated steel. And in many things, like a knife would be heat-treated steel. Old swords long ago would be heat-treated. An axe, a hatchet is a typical example. A hammerhead, typical example. The hammer has to be tough and hard but not shatter. So the selection of the steel is good. And because of this, many old things can be reused. And that's why I keep a good lot of stuff. It's very important not to keep everything. If you have an old scrap car, you might only need the half shafts out of it. You might need the rest. Don't hoard stuff to have it. But there are some things that will do. For example, if you need very thin carbon steel, inside in a chainsaw, where the bar goes, there are two flat pieces to keep where the chain goes between. And these are all made of good tool steel. And so if you wanted very fine springed steel, there is a handy source of it. Clock springs are another one that can be used as well. This process is very old. They were able to do it thousands of years ago. But for now, anyway, folks, I hope this shows. I'm going to leave you here and go around. Remember again, ferrite, iron, perlite, iron with carbon, austenite, carbon, iron with carbon is steel, carbon with iron or steel, heated above its critical temperature, austenite. Freeze, dry it, cool it very fast. You freeze the carbon in solution, you have martensite. Heat the martensite, it returns by proportion of the temperature to a mix of perlite and martensite. And that is a very tough material and can be used for lots of things. That's the carbon steel range. That's a good enough video. I'm going round now, and I hope I was going to do one thing. If I'm still here, I might pause this and heat or I might do it again. I think I'll just put this video in the can. If you heat that piece over there that I showed you with the martensite, you'll convert it down to a more perlite mix. We'll see you, right? Okay.